You all know Dr. Safo, but I think for people on the web, Professor Safo is a faculty member in the Department of Medicinal Chemistry. He's a structural biologist, especially he's been doing a whole lot of work on crystal structure of hemoglobin. And he's become interested in structural biology of GAG protein interactions. So he already has a couple of papers on that. So we are fortunate to have him here give us his perspective on structural biology of how GAGs recognize proteins. Right?
Okay, Hans, sorry.
Can we move it away?
Yeah, how do I do that? I don't want to.
He's lecturing here for the first time, so.
Okay, back.
It's okay.
It's okay, okay.
Yeah.
Let me try one more time. Okay, good afternoon, everybody. Okay, so for the next hour or so, 2 hours, we're going to be looking at interactions between GAG and GAG binding proteins, how GAG actually recognize these numerous proteins. And now, GAGs, as we know, as you all know, have the different diverse functional activities, and they do so by interacting with several GAG binding proteins. Now, all of these GAGs, most of these GAGs have carboxylate or sulfate moieties that are sitting dots to interact with many proteins that have basic residues, either in the active site or on the surface of the protein. However, this does not happen. There is an order in the GAG interactions with these proteins in terms of specificity, affinity, and recognition. So the question is, how does this happen? If you have a sulfate group, a carboxylate group, supposed to react with any protein that have what? Basic amino acid, but it doesn't happen. And that is what we're going to be looking at today. And by the way, I made some slight changes to my presentation, so some of them you see that there are additional material, and if you like, I can send them, post them again, but very minimal. Okay, so this is a short introduction of GAGs, and I'm sure you all know this. So basically it's repeating units of hexox and acidic sugar and hexoamine, which is the amino sugar. It's a repeating unit. And there are 5 different GAGs, 5 different classes of GAGs. And these differ in the type of the uronic acid or the sugar, the amino sugar. Now, they also differ in the type of the glycosidic bond. And this is very important because the type of the glycosidic bond or the type of the sugar molecule really allow these GAGs to recognize different proteins. And as we will see, okay? In addition, the monosaccharides are also decorated with phosphate, with sulfate, carboxylate, amines, and acetyl group. Okay? These also are important for GAGs to recognize different proteins. Now, although each GAG has a predominant disaccharide group, okay, however, there are several heterogeneity in case of a molecular mass, disaccharide construction, and sulfation. Okay. And this is also very important because if you look at heparin, okay, heparin isolated from different places may have a different mass, they may have different disaccharide construction and sulfation. And very important because this heterogeneity allow heparin to also bind to different heparins to bind to different proteins. And we're going to look at specific examples of these. These are examples of proteins or enzymes that utilize GAGs for activity. And I'm going to use some of these proteins as an example to illustrate how GAGs interact with these proteins. So first, let's take a look at some of the important characteristic features of GAG protein interactions. First, as I pointed out, most GAGs contain carboxylate and sulfate group, which are the driving force for the interaction with these GAG binding proteins. The GAG binding proteins, most of them also contain what? Basic group, and mostly arginine and lysine, and sometimes histidine. So these are ionic interaction actually drives this interaction between the GAG and the proteins. Now, the arginine, if you compare arginine interaction with the sulfate or carboxylate to lysine interaction, the arginine interaction is stronger than the lysine. And we will see the reason why. So let's illustrate these 2 points with some specific examples. Here I show interaction between antithrombin and a pentasaccharide of heparin. Antithrombin, as you all know, is very important in the coagulation cascade. So basically, if you look at the interaction between the antithrombin and the pentasaccharide of the heparin, most of the interaction is mediated by what? Sorbate. So you have 1, 2, 3, 4, 5. So it's a mixture of what? Lysine and arginine that are involved in sorbate or ionic or electrostatic interactions. And this is typical of most GAG protein interactions. Now, majority of these interactions, involve 4 to 7 basic residues. 4 to 7 basic residues. However, there are certain interactions, that are less, maybe 2 or 3, and others are more, 8 and 9. Now, these ionic interactions, especially if we consider heparin and antithrombin, contributes about 40% of the binding energy, and the remaining 60% is contributed by non-ionic interaction. These include hydrogen bonding, also hydrophobic interactions, and van der Waals interactions. So even though the ionic interactions are very, very important, very important, other interactions beyond ionic interactions are also required, to stabilize the interaction between GAG and these GAG binding proteins. Now, if you look, why is interaction with arginine more stronger than interaction with lysine? The reason is obvious here. This is the ammonium group. When you proteinate lysine, it becomes an ammonium ion. So it can only make one salt bridge interaction, ionic interaction. It can also, if it's hydrogen mediated, then it becomes a hydrogen bond. So, however, if you look at the guanidino group of arginine, it contains 3 nitrogens, each of them capable of making interaction with what? The carboxylate or the sulfate. So let's take a typical example. If we have a carboxylate or a sulfate coming in, the can react with these two amines. Okay? So this is what we see as a bidentate interaction. Or it can react with these two amines also. Yeah. It's also a bidentate. So in terms of ionic interaction with arginine, you usually get what? A bidentate interaction. With lysine, you only get one interaction. So basically, the ionic interaction with arginine is stronger than with lysine. Now, in the previous slide, I said that in some of these GAG interaction, GAG protein interaction, we have about 4 to 7 basic residues. Yes, you may have all these basic residues, maybe 8, maybe 9, but not all these basic residues are involved in the interactions. Some of them you may have 4, but only 2 may be involved in the interaction. So when you look at the affinity between the GAG and the protein, it's not usually correlate with the number of basic residues. Okay. Rather, it's combination of the basic residue interaction as well as other interaction with hydropathic residues that involve hydrogen bonding, van der Waals, and hydrophobic interactions. Now, for example, if we look at the growth factor receptor 1, okay, FGFR1, thrombin, or rate, these proteins contain how many basic residues? 7, as much as 7. However, they don't have the same affinity with heparin. They range from 0.3 nanometers to 7 micromolar, nanomolar to 7 micromolar. So it's not the number of basic residue, okay, that dictates the binding affinity. It's rather, as you will see later, it's rather how many of them are actually involved in the interaction. Okay. There are other heparin binding sites that contain only 4 basic residues. However, they have a very high affinity with the GAG. And the reason is all these 4 basic residues may be involved in the interaction. And also, in addition, you may also have other interactions, van der Waals, hydrophobic interaction, that also contribute to these interactions. So now let's go down to other important features of GAG protein interactions. We've talked about arginine and lysine as very important in driving, as a force in driving these interactions. However, there are other interactions, as I pointed out, also very important. Asparagine, glutamine, and histidine, they also play critical roles in the GAG protein interaction, and they involve hydrogen bonding. There are also other interactions, it's already pointed out, van der Waals, hydrogen bonding, and hydrophobic interactions. These are with the sugar backbone. In addition, serine, glycine, and all these small amino acids, sometimes they are very important because they allow these GAGs to approach the binding site with very minimal steric constraint and flexibility. And this got to do with how these some of these GAGs recognize these proteins. Sometimes if you have, they may have the same number of basic amino acid, the same type and the same number. However, they may have other amino acids that are very big, okay, and they prevent these GAGs from coming and binding to this site. Okay. So when you have serine and glycine, they allow minimal steric interaction, okay, and they that they usually are involved in specificity and recognition. Now, let's illustrate these points with some specific examples. Now, histidine. So we talk about arginine and lysine. However, histidine may also play a very important role in ionic interactions or hydrogen bonding. Here we have a histidine in this GAG binding protein, APLP1, which is a protein involved in the amyloid. It's an amyloid precursor like protein number 1. It plays a very important role in synapse organization. If you look at the active site, it has 5 histidines, okay, that make either direct hydrogen bonding or water-mediated interaction with the GAG. So if you look here, you have 1, 2, 3, 4, 5 that are acting in similar fashion as what? A lysine or arginine. Okay? Now, all these histidines are very important if you start making a side mutation. You take 1 out, you reduce the binding affinity. You take 2, you even reduce it even further. So these histidines, like the arginine and the lysines, are very important. And some of these GAG binding proteins utilize histidine. They may utilize a mix of histidine and arginine. However, some of them utilize mainly histidines for interactions. What about asparagine and glutamate? These are also very important. They are usually involved in the hydrogen bond interaction. Now, unlike histidine and arginine and lysine, which have been studied extensively, okay, these interactions were overlooked, and it's not until recently that people began to realize that they also contribute significantly to the GAG binding. So if you start making side mutation, you realize that these amino acids also contribute significantly to the binding. And an example is FGF. Okay, you have asparagine 114, and then you have glutamine 127. You make a mutation of asparagine to a glycine, you reduce the binding. Same thing happens with the glutamine. You make a mutation to glycine, you also reduce the binding. So these amino acids, even though they are not involved in ionic interaction, they are also very important in the GAG interaction. Now, let's take a look at the other structural features that also make GAG recognized and also involved in specificity. Okay. So, for the first 4 that we talk about, we mainly discuss about affinity, okay, interaction. However, the last 3 characteristics, these are really that make GAG able to recognize the proteins and also involved in specificity. Now, the topology and distribution of the basic amino acids on the protein itself, okay, the binding site, influences the specificity and recognition of GAG sequences. Also, in addition, the topology sequence, monosaccharide modification, the type of modification, the type and the geometry of the glycosidic bond also influence recognition of GAG binding protein. So let's take specific examples. Now, in the beginning, as I said, you have all these proteins that have basic residues. How come they don't bind to that? And the reason is, one of the reasons is the GAG bind to certain sequence, okay? They have to have, this GAG protein have to have a motif, a certain motif in order to attract these GAGs. Some of these motifs are shown here. X, B, B, X, B, X. Okay? So X is any residue like asparagine, serine, alanine, glycine, isoleucine, leucine, and tyrosine. B is the basic residues. So you have several of these motifs, okay, which allow GAG to recognize the protein. If you don't have these motifs, even though you may have basic residue, GAG cannot recognize. It's not a simple matter of the GAG coming in and binding to the basic residues. They come in, they have to have some orientation, okay, in order to be able to bind. And these motifs are very important in allowing such orientation to take place. And we will look at how these orientations come about. Now, if you look at these motifs, even though we have 3 basic residues, here we have 4, and here we may have 8. Not all of these basic residues are involved in the GAG binding site. Usually, the basic residues that are involved are separated by what? 20 angstroms. So you may have 10 basic residues or 4. Okay? Only the basic residues that are separated by 20 angstroms are usually involved in what? Interaction with the GAG. So here we have this sequence, the motif, lysine, arginine, lysine, lysine, arginine. Not all of these are involved in interacting with the GAG. Only a few of them, okay, approximately separated by 20 angstrom. Same thing with this. Okay. And so if you have a lot of residues, basic residues, and they are all very close together, okay, even though they are basic and even though they may attract the GAG, they cannot bind. Once it gets there, the orientation cannot occur in order for the GAG to optimize binding to the GAG binding proteins. Now, also, the type of the N or oxygen length sulfate group and the N length acetyl groups are also very important, okay, for attracting these GAG binding proteins. If they are not located at the right position, if you don't have the right number of the N or oxygen length sulfate group, the interactions are very weak and it's not stabilized. Okay, so you have to have the right proportion and the right sequence of this in order to be able to interact with the GAGs. The length and sequence of the GAG also influences specificity and recognition. What happens is if you have a very short GAG chain, okay, it goes into the binding site. It needs to change conformation in order to bind. So if you don't have the right length, the conformational chain cannot occur, so it cannot bind very well. If you don't have the right sequence, the conformational chain may occur, but it cannot bind to the, it cannot register with the GAG binding protein. So you have to have the right length and the right sequence in order to match with the GAG binding proteins. Okay. Not only the ionic interaction, it also involves the van der Waals contact as well as the hydrophobic interaction. So you have to have the right sequence, you have to have the right length in order to match the GAG with the GAG binding protein, basic amino acids. And one thing very important, once the GAG binds, there has to be a conformational change in the GAG. which is located at the glycosidic linkage. So this conformational change occurs at the glycosidic bond, okay, which allows the GAG to maximize binding and affinity. Okay. So there has to be a conformational change. The GAG has to orient in a certain way, and it occurs around the glycosidic bond. If there is no kinking, okay, there's no change in the glycosidic bond, then you don't get a kinking and you don't get maximal binding or affinity. We'll talk more about this in the next slide. So why is kinking very important in GAG recognition of these proteins? So let's take, for instance, heparin and a GAG binding protein. So you have the GAG, okay, coming in to bind to this protein. Okay. Normally, these GAG binding proteins, the binding site are characterized by loops, okay? Loops and a very shallow binding cavity. What GAG has to do is to be able to fill this shallow cavity and also register with these positive charges, okay, the basic residues. Okay. So you have your sulfate or you have your carboxylate. It comes in, it needs to register with these basic residues. How does it do that? There has to be a kinking, okay, in the GAG sequence. And where does the kinking occurs? It occurs in the glycosidic bond. So if you take, for instance, this GAG, it comes in, there is a kinking here, which allows this to fit in nicely to the binding site. So this is the glycosidic bond, and there's a rotation at the glycosidic bond, which allows the kinking to occur, and then allows this to bind optimally. So if you don't have the right sequence, okay, of the protein, okay, or the sequence, the right amino acid sequence at the binding site, you don't have the right monosaccharide sequence in the GAG, you cannot induce the kinking. Okay, the kinking has to be induced for the GAG to be able to fit nicely into the active site and to maximize interaction. Now let's take a specific example with the heparin and antithrombin interactions. So here you have a heparin, which is a very long saccharide. Okay. However, only the pentasaccharide, only 5 of the monosaccharide binds to the antithrombin. It's very important. This auto oxygen sulfate group is the sulfate that actually drives the interaction, and it makes interaction with the lysine 114. Lysine 114. And how does this happen? It only happens because of this kinking. So what happens is you have GAG coming in. Okay. The GAG comes in, and let's assume this is 114. Okay, it's 114, and you have your 3O sulfate group at this position. Okay, there has to be a kink in this position in order to place this 3O sulfate group at this position in order to register the interaction. So if there is an amino acid group here, very long amino acid group here, which prevents this kinking, okay, from registering, okay, then you're not going to get interaction between the 3O sulfate group and this lysine 114, which means this heparin cannot recognize the antithrombin. So it's very, very important that you have a kinking in the glycosidic bond that allows this group in order to interact with lysine 114. Without a kinking, this does not happen. And this interaction alone contributes to about 60% of the binding free energy of heparin and antithrombin interaction. In addition to this interaction, this very important interaction, what a kinking does is to place this monosaccharide close to lysine 125, which makes also interaction, which also stabilizes the interaction between the GAG, between the heparin and the antithrombin. So I've gone through all this in the previous. Now, let's compare this kinking between thrombin. So GAG can also bind to antithrombin at the same time, growth factor F2. They all recognize heparin. The question is, how do they interact with heparin? So if you look at the active side of both, antithrombin and growth factor, okay, they are very similar. However, there are slight differences, and this leads to different kinking. If you look at the heparin binding to antithrombin, there's only one kinking that places the 3O sulfate group close to the lysine 114. What happens is, in the same manner, if you have the heparin bound to the growth factor, what happens is, because of the slight differences, this group, the NS6O sulfate group, is well like the hexyl, and the 2O sulfate groups are able to come close to these amino acids, to the basic amino acid, because of slight different kinking, which leads to, there are here, instead of one kinking, which is found in the heparin, when it binds to the antithrombin, there are two kinkings here, which allows this NS6O and the 2O sulfate group to come close together to the basic residues and make interaction. So the take-home message is, when these heparins bind to different proteins, they induce different kinkings, which allow these heparins to recognize different proteins. Now, another example with the growth factor FGF. Okay, there are several. It's a growth factor. It's a family of growth factor. There are several types of growth factors. Okay, about 12 of them known. All of these bind to heparin. Okay, they are all involved in different activities. However, they all require heparin for the activity. And how does heparin recognize these different growth factors? And the answer comes through the crystal structure of one of these growth factors with heparin. Okay. So this growth factor, when bind to heparin, is dimerized. Okay. So you have the growth factor here, which binds to heparin. So it binds here, and then binds to this, which dimerize it, and it's able to interact. This whole thing, dimer is able to interact with tyrosine kinase receptors, okay, that leads to cell signaling during growth and development. The question is, how does heparin recognize all these 12 known growth factors? And the answer is due to the fact that all these growth factors have what? Different, slightly different loops, okay? they have slightly different loops, and also they have slightly different binding site. Okay? So when the heparins come in, okay, they all induce different kinks, and they are also able, and as a result, they are able to do what? Recognize the different growth factors. And so, depending on the active site, and also depending on the loop structure, you induce different kinks, which is able to recognize different heparin molecules. Now, in the beginning, we've been talking mainly about basic residues, which is also augmented by arginine, asparagine, glutamine, histidine, and other small amino acids. However, in some of these proteins, in addition to these basic residues or these amino acids, there are other metals. There are metals that also help to really recognize some of these GAGs. Okay. An example is the calcium-dependent GAG binding protein, which is able to recognize GAG because if you look here, this GAG Annexin 2, okay, it contains lysine, okay, which is able to bind to the GAG. However, it also contains 2 calcium ions, which helps it to recognize a specific GAG. Okay. So not only is the basic residues, it also contains these metals, ions that are able to allow this protein to recognize specific GAG, specific GAGs. Now, the size of the GAG binding site and the number of basic residues also affect the recognition and the specificity. Not as much as the loop structure or the binding geometry. However, the size and the basic residue may also affect the specificity and recognition. Not as much, but they do also. Basically, what happens is you may have a very large size or a very small size, and they attract these GAGs. And once they attract it, there has to be a rearrangement. So depending on the size, whether small or big, you can have a rearrangement, and that helps to recognize a specific GAG. And if you compare some of these GAGs, let's say AGF and Annexin, okay? Even though they have a very small binding site, okay, they have a very high affinity interaction to some of these GAGs. Conversely, you have some of these proteins with a very large binding site. However, they have a very low affinity with these GAGs. Now let's take secondary structural elements. How does that bind to these proteins? In several proteins, non-GAG binding proteins, okay? If you look at the binding site, you will see the substrate bound to an active site may be made by one secondary structure, okay? The active site may be made by one second, or maybe a multiple, but they are very close together. However, in GAGs, if you look at the binding site, it's made up by different secondary structures, all located at different positions. Okay? So you may have a helix, you may have a loop, and you may have also a beta strand. Okay? They are located at very, very different positions. Okay? And an example is shown here. You have a helix, you have the loop structure, you have the helix, you have the loop structure. And the loops are very important. All the GAG binding protein, you see a lot of loops. And the reason is the loop allows what? The loops are very flexible, which allows the GAG to do what? Able to fit optimum at this binding site. Now let's take an example of how thrombin and antithrombin is able to be inhibited by antithrombin. Okay. Now, when thrombin binds to antithrombin, the interaction is very, very weak. Okay, it's very weak. It requires heparin to bind to the antithrombin before thrombin can bind with a very high affinity, which is about 200-fold rate to the thrombin, in order to inhibit the thrombin activity. Okay. How does this occur? It occurs with binding of pentasaccharide of the heparin first to the antithrombin, which leads to activation of the antithrombin. There is a loop here which is able to interact with the thrombin, okay, forms a complex, and in doing so inhibit the thrombin activity. And as we've seen here, shown previously, this 3-O sulfate group is very important for the interaction of the pentasaccharide. Okay. So we need this to bind to the antithrombin in order to make it active to bind to the thrombin. Not only that, when the pentasaccharide approaches the antithrombin, there is also rearrangement of the binding site of the antithrombin. Okay? There has to be a rearrangement for the pentasaccharide to be able to fit snugly at the active site and make interaction with the active site. So you can see that several of these side chain amino acids are moved in order to accommodate the pentasaccharide. So basically you have your pentasaccharide of the heparin, which binds to the antithrombin, which leads to this reactive center loop. It's inactive conformation. Okay, when it's not bound to the pentasaccharide, it's in inactive conformation. Once it binds to the pentasaccharide, this assumes an active conformation, which is able to bind to the thrombin, and then parts of the rest of the heparin also binds to the thrombin, which then leads to inactivation of the thrombin. So these are the specific interaction between the thrombin and the antithrombin. Now, if you look at the interaction between thrombin, even though you have several, the number of basic residues at the thrombin binding site are more than found at the antithrombin site. Not all the basic amino acid is shown here anyway. You have more basic residue at the thrombin binding site than at the antithrombin site. The interaction at the antithrombin is stronger, and the reason is more of the basic residues are involved in contact with the GAG than the interaction between the GAG and the thrombin. So these are the specific interactions. I will skip. Now, if you look at how heparin binds to antithrombin, this antithrombin is inactive conformation. Okay, it doesn't bind to thrombin. It doesn't bind to any other molecule until it's activated. So it binds to the heparin, okay, and then this flips out, becomes activated. So it's able to bind to other proteases, okay? However, other heparin antithrombin-like proteins, this conformation is in active form, is able to do what? Bind to what? Bind to thrombin and able to inhibit thrombin. So the heparin here is acting as what? An allosteric effector. Because binding of the heparin leads to what? Activation of the antithrombin, okay, in order to be able to bind to the thrombin. Okay, in order to bind to the thrombin. So this is acting as an allosteric effector. Other serpins, they are already activated, so they are able to do what? Bind to thrombin. Okay, they are able to bind to thrombin or other proteases. Now, there are several proteins also known as hyaluronics. Okay, these requires hyaluronic GAGs for their activities. Okay. Now, the animal studies of hyaluronic GAGs have shown that these in solution occurs in varying conformation. Several conformation of this uronic GAG, okay, and it's believed that different conformers of this uronic GAG is able to recognize the different hyaluronics. Okay, so this allows specificity because of these different conformers that exist in solution, and basically. If they are able to solve the crystal structure, that will throw some light on this and how these hyaluronics bind to this uronic acid. Protein C inhibitor and antithrombin chain length recognition. So in the previous slide, we saw how antithrombin, when it binds to a heparin, is able to bind to thrombin and inactivate its activity. You also have protein C, which can also inhibit thrombin. So how do these two compare? If you look at the interaction between thrombin and antithrombin, the active site or the binding site overlap each other. Okay. However, they are far apart. Okay. That's about 18 angstrom apart. Okay. Now, if you look at the thrombin and protein C inhibitor, they are very close. Okay. Both of these complexes, okay, are formed by what? Heparin. So here, only about 14 or less, about 14 oligosaccharide of the heparin are required to do what? Form the complex. In this case, here only 18. With the thrombin and the PCI requires 14. And the reason is the binding site of these two are very close, while the binding sites of these two are very far apart. Okay, so we'll stop here. Any questions? Yeah.
Could you make a couple slides actually to the, I think it's when there's like a reactive center loop on antithrombin, it might have been, that actually pops up when it's active. Yeah, right there. All right. So this slide right here. So when that pentasaccharide binds, so it has to kink, and I guess, is there like a certain like secondary structural element that like pushes the reactive center loop up or something? Is that?
So basically, it's like typical of all allosteric effectors. Okay? Sometimes you bind to a certain part of the protein, and then it relays message throughout the protein. Okay, so message maybe about 10 angstrom away, 20, even 40 angstroms away. Because when you bind to one residue, you may break a salt break. Okay, if you break a salt break, then the other amino acid may move, which will then impact on another amino acid, and then there's a cascade of message that goes through the protein, and then it's registered. So based on similar thing happens here. You bind here, there's a cascade of structural changes that manifest in this this move to just flip up in order for the arginine to come up and able to bind to the thrombin. So basically that is why this pentasaccharide or heparin is also called an allosteric effector of antithrombin. Any more questions? Okay. Okay, I'm done. Okay. Yeah.
No, I don't have any more questions. I was just wondering.
What?
So that's it? End of lecture?
Yeah, that's it. Yes. Yep.
Alright.
So you guys are off. Yep.
And what about online? I don't know if anybody online has questions. No, me.
Okay, questions. How do I get them to? Do they hear me?
They can hear you.
Oh, anybody has questions online?